What I'd like to do is go through an example. I'm going to do this example and talk about practical limits where we simply use the stoichiometry. On Friday, we'll do another example. Probably use breakout groups on Friday, break things up a little bit. But hopefully by going through this example where we're actually simply looking at the stoichiometry, it'll give you a sense of the types of reactions or the types of calculations that we need to do with these softening reactions. So we have a water. We're given the water quality, and it has 100 milligrams per liter of CO2. It has 110 milligrams per liter of calcium, 31 milligrams per liter of magnesium, and 320 milligrams per liter of bicarbonate, and these are reported as the ion. You're told that you're designing a water treatment plant with a design flow of 4 times 10 to the 4 cubic meters per day. And you're asked to determine the lime and soda ash doses to meet practical limits. This means we are looking at the stoichiometry. Look at the stoichiometry and the stoichiometry only. So I've tabulated the data here. This is the starting data. So this is the data you're given. The next thing we want to do is calculate the molecular weight, or look up the atomic weight. So I have the atomic weights or the molecular weights for these compounds. We have calcium, we have magnesium, bicarbonate, and CO2. The next thing we want to do is calculate the concentration in, and I've given it in millimoles. So for example, we have calcium 2 plus, we have a concentration of 100 milligrams per liter. We'll divide that by 40.1 milligrams per millimole. Milligrams cancel, and we have 2.74 millimoles per liter, or 2.74 millimolar. So we do the same calculations for magnesium, bicarbonate, and CO2. The next thing we need to do is determine the number of equivalents. So I've mentioned before, the number of equivalents will typically be the charge on the species. So for calcium, it's easy to see, it's 2. For magnesium, it's 2. For bicarbonate, it's 1. And what about that CO2? Okay. Remember, CO2 reacts in water to form carbonic acid. Carbonic acid can donate 2 protons, so N is equal to 2. So you'll always use a 2 for CO2. And those of you in 481, it's the same thing there. So now we can calculate the equivalent weight. So let's use CO2. We have a molecular weight of 44 milligrams per millimole. We divide that by 2 milliequivalents per millimole. Millimoles cancel, and that is 22 milligrams per milliequivalent. That is the equivalent weight of CO2. So we can do the same thing for the other species. We then want a concentration in milliequivalents per liter. So if we take that calcium, we have 110 milligrams per liter. We divide that by the equivalent weight. Milligrams cancel, and we have an equivalent weight of 5.48 milliequivalents per liter. Now we typically use milligrams per liter as calcium carbonate. So we multiply the concentration in milli equivalents per liter by 50 is right. So 50 milligrams per milli equivalent, okay, and that equals 274 milligrams per liter as calcium carbonate. So where did the 50 come from? This is the equivalent weight of calcium carbonate. The next thing we want to do is determine the total hardness, the carbonate hardness, and the non-carbonate hardness. And we're going to do that with a bar chart because it's a nice way of symbolically showing the concentrations. So let's start here. And this is 0. Not very good to scale, but this is our CO2. Typically, we'll draw the CO2 in this way, and the concentration is 227. So this is milligram, the concentration in milligrams per liter. Concentration of calcium, and we write these in the form of predominance. So calcium is of the cations, it's the highest concentration. So this is calcium. And then magnesium is here. And if we add the 128 plus the 274, this is 402. Okay? So all I've done is I've added, represents the 128. Now I can do the same for alkalinity. So my alkalinity is 262. So this is my bicarbonate. And the reason I can say that is because we said the pH was 7.3, and at a pH of 7, between 6 and 8, I can say that my alkalinity is approximately equal to my bicarbonate concentration. So I have my bicarbonate. All of the other ions here, we have to have other anions. So there are other anions that make up the charge balance. So if I look at this, my total hardness is equal to what? So the total the hardness, 402 exactly. It's the sum of the polyvalent cations. In this case, the only polyvalent cations you have are calcium and magnesium. So we sum those, it's 402. My carbonate hardness is equal to what? This was 262. And these are all in milligrams per liter as calcium carbonate.
Yeah.
Where does the 262 come from?
It's a smart investment.
It's that portion of your hardness that's associated with alkalinity.
Chiropractor is a lot more expensive.
Dr. Maston?
Yeah?
That part that you just highlighted, that relates to the carbonate hardness, right?
Correct.
Okay, thanks.
And if you are not muted, if you could make sure you mute yourself. So I just highlighted, okay, this is our carbonate hardness. So it's that portion of the calcium that's associated with bicarbonate. Then I'll highlight, let's pick a different color. This portion here corresponds to what? So the blue portion corresponds to, so yellow is carbonate hardness. The blue corresponds to what?
Total hardness?
The blue,
or non-carbonate hardness?
And non-carbonate hardness. So this is going to be my non-carbonate hardness. Okay. So I have 262 milligrams per liter as calcium carbonate of carbonate hardness, and I have my non-carbonate hardness is equal to 402 minus 262 or 140 milligrams per liter. So now I know my carbonate and my non-carbonate hardness. So now we need to look at how much lime we need to remove. So the first reaction is neutralization of CO2. That reaction is CO2 plus calcium hydroxide that we're adding, or we could write this in terms of calcium oxide. Reacts to form calcium carbonate, and these are the exact same reactions on the previous slide. Okay. We need to know how much CO2 we have in solution. So let's go back. We want this on a molar concentration. So we have 2.27. So we have 2.27 millimoles of CO2. So how many millimoles per liter of calcium hydroxide do we need? Exactly. 2.27 millimoles. How many millimoles per liter of calcium carbonate do we form? 2.27. The next reaction we need to think about is the carbonate hardness due to calcium. So the reaction we have is calcium. I'm just rewriting the reactions from previous page. And you do, well, there's no exams anyway, but even if there were, I wouldn't expect you to memorize these reactions. I'm just going to do ... to save time. Okay. So how much carbonate hardness do we have that's due to calcium? This is why our bar chart becomes really helpful. So let's look back. What we want to know is, what is the carbonate hardness due to calcium? So looking at your bar graph, or your bar chart, what is the carbonate hardness due to calcium? 262, exactly. Okay. So that was milligrams per liter. On a molar basis, it is 2.62 millimolar. So we need 2.62 millimolar, and we'll produce twice as much, 5.24 milli. I've got writing these as molar, okay? So that's the carbonate hardness due to calcium. The next reaction is the carbonate hardness due to magnesium. So let's go back. Let's look at the bar chart. How much carbonate hardness due to magnesium do we have? No, remember, okay, carbonate hardness corresponds to my bicarbonate. Good one. We have 0. Look at my magnesium. All of my magnesium is associated with other anions. So it's associated with non-carbonate hardness, not with bicarbonate or carbonate hardness. So this is 0, and we don't need to worry about carbonate hardness due to magnesium. Does that make sense?
Dr. Masson?
Mm-hmm.
Does magnesium only add to carbonate hardness when the bicarbonate is greater than the calcium ion concentration?
Mm-hmm. So we had the situation, I'll draw it below. So if we had the situation below where, for instance, this, I'm going to make sure I'm using the consistent colors. So if this were my bicarbonate concentration, then notice here I have more bicarbonate than I have carbonate. So more bicarbonate than I have calcium. So I have, in this case, all of my calcium here would be associated with bicarbonate, and I would have magnesium also associated with bicarbonate. So in this case, I would have carbonate hardness due to magnesium. But in the situation that I've given you, we have a deficiency, essentially, of bicarbonate compared to our hardness. So for that reason, my carbonate due to magnesium is equal to 0. The next reaction I want to look at is my non-carbonate hardness due to calcium. And here the reaction is calcium, plus we're adding soda ash now. Now let's go back and look at the bar chart. How much non-carbonate hardness due to calcium do I have? Exactly, 12. Okay, it's the difference between the 274 and the 262. It's only this portion right here. 0.12 millimolar. I need 0.12 millimolar of soda ash, and I produce 0.12 millimolar of calcium carbonate. If you don't mind, let's just do, we've got one more reaction and it won't take very long to finish this. So the last one we have is non-carbonate hardness due to magnesium. So we have magnesium, and there we're reacting that with lime plus soda ash. And now going back to this, all of our magnesium is due to non-carbonate hardness. All of the magnesium is due to non-carbonate hardness. So we have here 1.28 millimolar. We need 1.28 millimolar, and we need 1.28 millimolar. So when we calculate the amount of lime that we need, we needed 2.27. We needed 2.62. We didn't need any lime for the fourth reaction. We need 1.28 here. So we need 6.17 millimolar of lime. And soda ash, we need 0.12 millimolar plus 1.28, so we need 1.40 millimolar. So that gives us the amount of lime and the soda ash that we need. The last thing we need is you were told that the plant design flow is 4 times 10 to the 4 cubic meters per day. So if we take the concentration in moles per liter and we multiply that by the molecular weight, we actually add this as calcium oxide. So we'll multiply by this by grams per mole. We have to multiply this by 1,000 millimoles per mole. And we're going to multiply this by 4 times 10 to the 7 liters per day. For 1,000 grams per kilogram, and we need almost 1,400 kilograms per day. I'm going to leave you with that. I'm going to suggest, okay, between now and Friday, calculate the amount of soda ash that you would need, and we'll just do a quick check of that on Friday. Lastly, we'll calculate the mass of soda ash needed. We've calculated 1.4 millimolar. We then multiply that by 10 to the minus 3 moles per millimole, multiply that by the flow rate, and then convert from meters cubed to liters, multiply that by the molecular weight of sodium carbonate or soda ash, and then convert from grams to kilograms, yielding 6,020 kilograms per day. Finally, in summary, to soften to the practical limits, we need 13,900 kilograms per day of lime and 6,020 kilograms per day of soda ash.